No, don't do it! No, no, don't do it!
Daddy is a cokehead. Good morning, fellow mathematicians. Today we are going to make Nägel mit Köpfen. Yeah, that's what my grandma would say, probably. We're going to deal with this integral today, and basically a cute little variant. So this right here isn't the main star today. We are going to make a substitution and then we are going to have our main star, and I'm going to present you two ways to integrate this right here. Basically a quite classic way, and the other one is quite exotic but absolutely exciting. So we're going to start off with the really exciting way and then with the classic way. At first, like I said, I would like to introduce a little substitution. Let, for example, t be equal to, well, natural log of x, but with a negative sign. So negative natural log of x. So that comes in quite naturally. We want to get rid of this weird negative sign, this weird argument in the natural log. If we differentiate both sides, we are going to end up with dt being nothing but negative 1 over x dx. The cool thing is, we are going to get our 1 over x basically for free, because if we drag this negative sign into here as the exponent, that's natural log of 1 over x, and then if we take e, base e on both sides, we're going to end up with e to the t is nothing but 1 over x. Okay, so that's equivalent to saying we have dt is nothing but negative e to the t dx, and well, now we can multiply both sides by negative e to the negative t because it's not equal to 0, and then we are going to get dx is nothing but negative e to the negative t dt. And now we can plug this chunk into here. We are going to end up with, okay, if we plug 0 into here, our natural log is going to diverge to negative infinity, but negative and negative is positive, so positive infinity down here as the lower bound. And if we plug 1 into here, well, that's negative 0, this is nothing but 0. Then we have the natural log of t times our dx, our differential, which is nothing but negative e to the negative t integrated with respect to t. We can distribute this negative sign into here to turn around the upper and lower bounds to get an integral from 0 to infinity of e to the negative t natural log of t integrated with respect to t. And this is our main boy for today. This right here is a really famous integral that has probably been evaluated by Euler at first. I don't know, he basically evaluated every integral there is out there, so he was an absolute genius. Like I said, we are going to do it a really exotic way at first, using the Leibniz rule for integrals. I want you guys to consider something different for this purpose. I want you guys to consider our boy, the gamma function of, yeah, z. I don't know. Gamma function of z. This is nothing but the integral from 0 to infinity, we have derived this before, of, well, let's say t to the, yeah, t is a good variable for this matter, t to the z minus 1 times e to the negative t integrate with respect to t. And now we are going to differentiate both sides with respect to z. And for this purpose I would like to consider this t to the z minus 1 as nothing but e to the natural log of t to the z minus 1. We can bring the z minus 1 to the outside. So this is nothing but the natural log of t times z minus 1. Okay? That's the same expression, it's completely the same. Now, if we differentiate that, we are going to get that gamma prime of z is nothing but, okay, gamma prime of z is nothing but integral from 0 to infinity of the partial derivative of this integral, this integrand with respect to z. Okay, so our upper and lower bounds are independent of our variable z, meaning we can use the special case of the Leibniz rule for integrals. Also, well, our integral is strictly positive, our integrand, so we can Fubini this limit and take it to the inside. So that's the only condition really for the Leibniz rule for integrals. Also we have e to the negative t, and then we have t, or I'm going to put it like this, e to the natural log of t times z minus 1 integrated with respect to t. And well, e to the negative t is independent of z, so we can bring it to the outside. Differentiating this thing with respect to z is actually quite easy. We're going to end up with an integral running from 0 to infinity. E to the negative t stays as it is. This is the factor that we also have here, so absolutely Gucci. And then we have nothing but, if we differentiate that, we're going to drag the natural log of t down. Oh, natural log of t, that's also so damn nice. So we have this thing right here. And also, we let this thing as it is, so our exponential function is going to be preserved as always. We just have to use the regular chain rule. But this exponential function is nothing but t to the z minus 1. Integrated with respect to t. But doesn't that look quite familiar? So this integral is actually just this integral where we evaluate this gamma prime at z being equal to 1, because if we plug 1 into here, you see this is just going to be t to the 0th power for z equal to 1. It's nothing but, well, our integral from 0 to infinity of e to the negative t, natural log of t, integrated with respect to t. But here comes the big fucking question. What the fuck is gamma prime of 1? Our boy digamma function comes into play. Oh, I just love this boy. So, our digamma function of z. I'm going to write it here once again. It's nothing but gamma prime of z over gamma of z is nothing but negative our Euler-mascheroni constant plus the sum running from k equals to 1 to infinity of, okay, now I'm using the weird form that I have derived in this one video at the end, a little bit improvised, 1 over k minus 1 over k minus 1 plus z, if I remember correctly. Yeah, that should do the trick. Meaning if we multiply both sides by gamma of z, we're actually going to get our gamma prime of z. That's what I said. That's why I made the video on x factorial differentiated with respect to x. Now, what happens if we plug in z being equal to 1? Okay, here comes the real magic in. So, for z being equal to 1, I'm going to leave it as it is. This is gamma prime of 1 over gamma of 1. But gamma of 1 is 0 factorial, this is nothing but 1. So overall, we are going to end up with gamma prime of 1. Once again, I'm terribly sorry for my gamma, it looks fucking ugly. Is equal to, okay, negative Euler-mascheroni constant plus a sum running from k equals to 1 to infinity of 1 minus 1 is going to evaluate to 0. So we have 1 over k minus 1 over k. And this right here is a bloody amazing telescopic sum, which is going to evaluate to 0 overall. So we can say with a really gutes Gewissen that this thing right here, by our definition of the digamma function, is nothing but negative Euler-mascheroni constant. Yeah, coolio! So this way right here is also kind of a classic way, but it's just way more fabulous than the regular old, taking the limit stuff way. That's fucking amazing. Using the digamma function, and now for the pretty classic approach. So here comes the classic way, and if you haven't really derived the digamma function and stuff like this before, then this right here is kind of messy because it takes way longer, you could say, but it's still not too hard. So we know by now that this integral is bound to exist. It's going to converge to, well, negative Euler-mascheroni constant. Meaning we can also break this integral up right here. I would like to break it up into the integral from 0 to 1 of, well, e to the negative t, natural log of t, and also the other part plus the integral from 1 to infinity of, well, our integral once again, e to the negative t, natural log of t integrated with respect to t. And now we are going to handle those on its own. So I'm going to call this thing right here I1, and this right here is just our I2. We are going to deal with this one because it's way harder to evaluate, just because of some convergence problems. And for this we are going to make use of a little notation, a trick. I actually have this from Inside Interesting Integrals. You can also use the limit definition of the exponential function, but this way is way more beautiful actually. So I want you guys to consider the primitive of e to the negative t. So if you integrate e to the negative t, you're actually going to end up with negative e to the negative t plus some arbitrary constant c. Okay, meaning if we differentiate this primitive, we're going to end up with our e to the negative t once again. We can use any constant we want, but now I would like to consider this constant as being just 1. You can probably also make use of Taylor series expansion. I tried it out at first because I couldn't really get anywhere with any standard methods, kind of, but Taylor series gets really messy in the end, so don't try it out. We're going to deal with this. Okay, so e to the negative t is thus nothing but the derivative with respect to t, in this case, not x, of, well, negative e to the negative t plus 1. Okay, this is something we can do. And this plus 1 right here is going to save our s, because with this plus 1 we can actually get rid of all the convergence problems that we would otherwise get if we would just partially integrate this thing and just end up with negative e to the negative t. Try it out without this plus 1 and you are going to be fucked in the ass pretty hard. So, partially differentiating this first integral, we're going to integrate this thing right here, d dt, negative e to the negative t plus 1. And, well, we know if we integrate just this differential, it's going to be the function itself, so negative e to the negative t plus 1. And naturally we are going to differentiate the natural log of t because, well, yeah, it's just better how it works out that way. So this is going to give us 1 over t, multiplying this together and then taking this integral, okay? Then we are going to get for I1 that this is nothing but negative natural log of t, I'm going to bring this negative sign to the front, times, okay, if we drag the negative sign out, e to the negative t minus 1, then minus and minus becomes positive, so plus the integral from 0 to 1 of, this is going to give us 1 minus e to the negative t over t integrated with respect to t. I got rid of this negative sign right here, so we have e to the negative t minus 1. Okay, I factored out this negative sign right here. I hope you can see where this came from. This thing right here, we have to evaluate from 0 to 1, naturally, by doing partial integration. If we plug 1 into here, okay, I don't see any problem because this is just something finite and natural log of 1 is going to 0. Okay. But the second part of integration is where it's at. So that part is quite difficult because if we plug 0 into here, we are going to get 1 minus 1, which is 0, times negative infinity. Okay? Without this 1, we would get something finite times minus infinity. And in this case, we couldn't really make use of Papa L'Hopital, but with this notation, the trick right here to get our negative 1 extracted, we can actually use Papa L'Hopital and get rid of all the problems in the process.
No, don't do it! No, don't do it!
Meaning, after we have done this pile of crap, this actually goes to 0, leaving us with this thing right here as our I1. Now I would like to drag a negative 1 to the outside to bring it into a familiar form, namely negative integral from 0 to 1 of 1 minus e to the t over t integrated with respect to t. And now I don't have any space left, I'm going to see you in a second. Our I2 is way easier to evaluate. Just do regular integration by parts. So I'm going to go through the process once again. di plus minus differentiating e, the natural log of t gives us 1 over t. And then just simply integrating e to the negative t. No convergence problems there, negative e to the negative t. Multiplying this together, then taking the integral of this thing is going to give us 4i2, nothing but negative natural log of t e to the negative t from 1 to infinity, this time 1 to infinity, I'm terribly sorry. Minus and minus becomes positive, plus the integral from 1 to infinity of e to the negative t over t integrate with respect to t. And yeah, no problems here at all. If we plug 1 into here, it's going to give us 0 because natural log of 1 is 0. If we let this approach infinity, okay, it's negative infinity over infinity situation, but the exponential function grows way faster. So use L'Hopital once and you are done then. So that's just 0. This is just 0 in the limit, meaning we are going to end up with, yeah, plus this exponential integral. So that's equal to negative integral from 0 to 1, 1 minus e to the negative t over t, integrate with respect to t, plus integral from 1 to infinity of e to the negative t over t, integrate with respect to t. And this actually, if you factor out a negative 1, then this is going to be our Euler-mascheroni constant. That was the Putnam problem I covered before. So negative Euler-mascheroni constant. There was a lot of fucking work just because of this stupid ass L'Hopital crap that we had to do. But sometimes you just not get around without L'Hopital or something like this. So it can pose a real problem sometimes. So be careful what you do, my boys and girls. I think guys watching, if you did enjoy this video, please like, subscribe, recommend channel if you want to support channel a bit more by those t-shirts I created. For example, this trivial one. I love this t-shirt, it's so great. And here support channel on Patreon. Up until the next video, have a fappable day, my friend. Ciao.